Hi there. In this recording, I would like to show you the derivations for a charging and a discharging capacitor. So let's get to it. Let me share my screen here. All right, so here we go. So first, let's assume that we have a battery hooked to a capacitor and a resistor in series. And this is the standard setup that folks start with. Let's assume that we have our battery with an EMF, funky looking E there, and a capacitor C, and a resistor R. So this is a pretty generic type looking little circuit with a battery in series with a resistor and capacitor. Now, what we're going to say is that at t is equal to 0, the switch is closed. And the capacitor is initially uncharged. Okay, so we're just starting charging up the capacitor and there's no initial charge on it when that switch is closed. Now, what we'd like to know is what's going on with the capacitor while it's charging. It's not particularly interesting to us what happens at the very end. We know that what happens is when the switch closes, the capacitor is initially uncharged, and then current will start to flow clockwise through the circuit like so, and charge will build up on the capacitor plates. Positive charge will build up there on that left-hand plate. Negative charge will build up there on that right-hand plate. And this process will continue until the voltage across the plates of the capacitor equals the voltage supplied by the battery. And at that point, the capacitor is fully charged and it just sits there, right? And no more current flows in the circuit. So we're not terribly interested in what happens after that occurs, after the capacitor is completely charged. Right now, what we're looking at is what's happening while the capacitor is charging, what function is followed, and how does the charge on the capacitor depend on time. And so we're going to look at an intermediate time while it's in the middle of charging. So what I'm going to do is apply the loop rule here for our circuit. Remember that Kirchhoff's loop rule for circuit says that if you start and end at the same point in a single loop around a circuit, and you sum up all the changes in voltages as you walk around that loop, then the sum of those changes in voltage must be 0. So we're going to close our switch, and then we're going to look at the loop. Let's start here at the lower left-hand corner of our loop and walk around. So first, we're going across the battery from the ground to the positive terminal, and that causes an increase in voltage of plus the EMF of the battery. Next, we're going to drop voltage across the capacitor and the resistor. Now, remember that our equation for capacitance is C is equal to Q over delta V. So if we were to solve then for what the voltage drop across the capacitor plates was, and it would be Q over C. Now we're looking at some intermediate time, so I'm going to call this charge on the capacitor at that intermediate time Q prime. Okay, so this isn't the max charge built up on the capacitor, which of course would be equal to the EMF of the battery times the capacitance. So we're going to look at some Q prime time. So that means that as we walk across the capacitor plates, we're losing minus Q prime over C as we walk across with the voltage there. And then, of course, for a resistor, we apply the Ohm's law application there, and we know that the voltage drop across a resistor is minus I times R. And now we walk across our switch, which we ignore any resistance of that, and we're back to our starting point. And so our loop rule for our circuit is plus EMF of the battery minus Q prime over C minus IR is equal to 0. Okay. So there you go. Now, remember that the definition of current is the time derivative of the charge. So I can plug in for that. So I have plus EMF of the battery minus Q prime over C minus dQ prime dt times R is equal to 0. Okay, now what we want is an expression for the charge on the capacitor plates as a function of time. And so we want Q prime as a function of time, or we want Q as a function of time. This is, however, a first order differential equation. And so what we need to do is to rearrange this equation, get everything with variable Q prime on one side of the equation, things with T on the other side of the equation, integrate both sides and solve. And that's how you solve a first order differential equation. So let's go through the algebra and the techniques to solve that kind of problem. So first of all, I'm going to go ahead and divide everything through by the resistor of the battery, EMF over R minus Q prime over RC minus dQ dt is equal to 0. Okay, now next I'm going to want to multiply and get rid of this dt here in the bottom of my dQ dt. So first step, I'm going to take my dQ dt over to the other side of the equation. EMF over R minus Q prime over RC is equal to dQ prime dt. Okay. And now what I can do is I can multiply both sides of the equation here by dt. And that moves that dt over to the opposite side of the equation for my dq. Like so. Okay. Now, I'm going to go ahead and factor out 1 over RC from the parenthesis here on the left-hand side. So that gives me dt over RC. And then that leaves EMF times the C minus Q prime. Like so. Now, I'd like to get the Q prime here in the parentheses on the same side as my dQ prime. Okay, so that gives me dt over RC is equal to dQ prime over C times EMF minus Q prime. All right, so now I've done it. I've isolated everything that depends upon Q and put that on one side of my equation. And now I've got the stuff that got time dependence on the other side of the equation. Okay, and now I'm going to integrate both the left and the right hand side, and then I'll have my expression for Q right after a little bit of algebra. So that's our strategy. Okay, so let's go ahead and take this to the next slide and copy that over and then solve. So I have dt over RC is equal to dq over C times the EMF minus Q prime. Now I'm going to integrate both sides. Boom, boom. So what are my limits of integration here? Well, on the left-hand side, I'm integrating over time. So I'm going to start at t is equal to 0 when I close my switch, and I'm going to end at some later time. But I want it to be in the middle of charging, so it's just a random point. I'm just going to call it t. Now on the right-hand side, I'm going to integrate from no charge on the capacitor, starting off at t is equal to 0, no charge was there, to some charge q in the later time, where it's not all the way charged, but say it's in the middle of charging. So that's what I'm going to do. Now on the left-hand side, R and C are constants, so they get pulled out of the integral. So I just have 1 over RC, integral from 0 to t of dt, and that's just 1 over RC times t, integrated from 0 to t, which is t over RC. So the left-hand side integration is pretty straightforward, not too bad at all. Now for the right-hand side, I'm going to have to do a little bit of a substitution. So the substitution I'm going to use is I'm going to let y, I could pick any variable, but I just chose y, equal to C times the EMF minus Q prime. And then dy is minus dQ prime, because C times the EMF, those are constants, right? So then that means that on my left-hand side, I'm integrating minus dy over y. And that gives me, of course, negative natural log of y. Okay, so now I'm going to plug back in for y and then evaluate at the limits of my integration. So I have t over RC, and then that's going to be equal to minus the natural log of C times the EMF minus Q prime, evaluated from 0 to Q. Okay, so that's pretty straightforward. All right, so I have minus sign here, and then the natural log of C times the EMF minus Q minus the natural log of C times the EMF. All right. Okay, so what I'm going to do now is take that minus sign over the other side. So I have minus t over RC is equal to, and now looking here, I have on the right-hand side subtracting natural logs. Now, when I subtract natural logs, it's the same thing as dividing their arguments. So that could be written as the natural log of C times the EMF divided by minus Q divided by C times EMF. Sorry, that handwriting is terrible. Let me fix that. Okay, and so that's what we've got. Now, we don't like to leave natural logs alone, right? We'd rather have things in terms of exponents. So if I want to get rid of my natural log, I'm going to raise both sides to the power e. So I have e to the minus t over RC is equal to C times the EMF minus Q over C times the EMF. Okay, so now I'm going to multiply both sides here by C times the EMF. So I have C times the EMF minus Q is equal to C times the EMF e to the minus T over RC. And now I can go ahead and solve for Q. So I have C times the EMF minus C times the EMF e to the minus T over RC is equal to Q. So I can factor out C times the EMF, and that is my expression for the charge on the capacitor as a function of time. So there we go, we did it, okay? So now let's think about this expression for just a second. If we set T is equal to 0, then that means that in my exponent here, e to the minus T over RC, okay, this bit, I have e to the 0. And so e to the 0 is 1, and 1 minus 1 is 0. So, of course, it tells us that the charge on the capacitor is equal to 0 at T is equal to 0. Now, over time, as T goes to infinity, this e to the minus T over RC, well, that goes to 0, okay? And so then I just have C times the EMF times 1 minus 0, or 1. And so the charge as T goes to infinity is going to equal to the capacitance of the capacitor times the EMF of the battery, okay, which is the max charge that capacitor can hold. So Q max is equal to C times the EMF, okay? And that's the charge at T goes to infinity when the capacitor is fully charged, okay? So if we were to plot what this looked like, then we would get an increasing exponential. So here's Q versus T, starting out at 0 and going up to Q max, which is equal to C times the battery's EMF. Okay, so it's an increasing exponential function. So that's what's going on with a charging capacitor. Now, that's the charge, but sometimes we'd like to figure out what the current is because, you know, the current is easily measured with an ammeter, and so we can monitor what's going on with the current in time. So let's look at this expression here. Remember that the current I is equal to dq dt. And so if I take the time derivative of Q, then I have ddt of C times the EMF times 1 minus e to the minus T over RC, right? Okay, so taking the time derivative of that, C times the EMF, that's the constant. So that C times the EMF, that goes to 0 when you take your derivative. And then now you're taking the derivative of the second term in the expression, which is minus C times the EMF times e to the minus T over RC. Okay, so when I do that, I have minus C times the EMF over minus RC times e to the minus T over RC. So the C's cancel out, the minus signs cancel out, and I just have the EMF over R e to the minus T over RC. So, whoops, that's the current with respect to time. Okay, so if you think about what happens to the current, let's plot that. So it's going to start off at maximum value at T is equal to 0. At the maximum value, maximum value will be the EMF of the battery over R, like the capacitor wasn't even there and there was just a resistor in the circuit. And then as T goes to infinity, then the current will go to 0. And so you see here that we have an exponential decay for the current with respect to time. Sorry, my drawing skills aren't lovely, but there you have it. An exponential decay. Okay. All right, so that's a charging capacitor. Now let's talk about what happens to a discharging capacitor in a circuit, okay? So in that case, there's not going to be a battery, and you're just going to have a capacitor, which is all charged up in series with a battery and a switch. Okay, so here's your capacitor, here's your resistor. You're going to have a positive plate and a negative plate built up on your capacitor. Now, at time T is equal to 0, you have Q max on your capacitor. In other words, it was all charged up by some battery or something, and then the battery was disconnected, leaving only the resistor and the capacitor in series in the circuit. And at T is equal to 0, you have that max charge on the capacitor, and then the switch is closed. And at that point, the capacitor starts to act as the source of EMF for the circuit, right? So it's powering your circuit, okay? Now, what happens is the current is going to leave from the positive plate of the capacitor and flow away. So that's going to be the direction that the current flows in that circuit. It's going to go clockwise here. Okay. Hang on just a second. Sorry, had a delivery. Okay. All right. So one thing here. Normally, when you have a capacitor in a circuit, like when we had this capacitor back here, okay, the current is going to flow towards the positive charge plate. In other words, it leaves the battery, right? The current flows away from the positive terminal of the battery and starts building up on that plate on the left there, which then accrues positive charge, and then negative charge accrues on the other plate. So you can see here that in this charging capacitor scenario, the current is flowing towards the positive plate of the capacitor. But when the capacitor acts as the source of voltage for a circuit, what's going to happen is the current flows the other way. It flows away from that positively charged plate, okay? So the current is going to flow opposite okay? It's going to flow in the opposite direction that it does for a charging capacitor. So that's going to mean that the direction of current is going to flip the sign. And so what we're going to have for our loop rule here is a flip of the sign. So in other words, you've got a gain of Q prime over C as you go across the capacitor, right? And then compared to the charging capacitor, you're flowing in the opposite direction, which makes that minus IR into a plus IR there, okay? And then that is going to equal to 0, okay? So that's our loop rule then for our discharging capacitor. All right, so now let's take this and write it in terms of our differential equation expression. Okay, so that's that. All right, so now if we rearrange this equation, what we're going to do is put everything with dq prime on one side and everything with dt on the other. So here we have, we're going to do a little bit of algebra to get there though. Okay, so there's that. Now let's divide out both sides by r. Like so, okay. And now let's go ahead and put all the q's on one side and everything without q on the other. So we have dt over rc is equal to minus dq prime over q prime. Okay, so here we are. And now what we're going to do is we're going to integrate both sides of this equation and solve for the charge on the capacitor as a function of time, just like we did with our previous example. Okay, so let's get to it. We have dt over rc. We're going to integrate that. And then we have minus dq prime over q prime. We're going to integrate that. Now, just like before, we're going to integrate from time 0 to t because we're starting our clock when the switch closes, and that's when the capacitor starts to power the circuit. However, remember that on the right-hand side, you're starting off with the max charge on the capacitor, okay? And we're going to some random time later. We don't know what the charge is at that point. We know it's not going to be the max. It'll be some intermediate value as the charge bleeds off, okay? So the limits of integration on the left are 0 to t, and the limits of integration on the right are q max to q. Okay, so just like before, this integral on the left-hand side is pretty straightforward. 1 over RC is a constant, and then you're just integrating dt, and that just gives you t, which you evaluate from 0 to t, which is t over RC. So just like before, we have that left-hand side being t over RC. Now, on the right-hand side, however, we have the integral of dq prime over q prime, and that gives us the natural log of q. So here we have minus the natural log of q prime, and we're evaluating that from q max to q. Let's go ahead and move that negative sign over to the other side of the equation so that it makes it a little easier to deal with. And then we have the natural log of q minus the natural log of q max. Okay. All right, and just like before, when you subtract logarithms, it's the same thing as dividing their arguments And so there you go. Okay, well, we still don't want a logarithm there, so we're going to raise both sides to the power of e, like that. And then finally, we can solve for the charge as a function of time, and Q will be equal to Q max times e to the minus t over RC. So there's our expression for the charge on a capacitor that's powering a circuit, okay? So what's going to happen is there's going to be an exponential decay of the charge here. So it'll start off at its maximum value, Q max, and exponentially decay. Let's draw that. So here's Q versus T. Here's my value, Q max. And then I have the exponential decay, like so, okay? So there it goes. And as time t goes to infinity, then the exponent there will go to 0. And at that point, the capacitor is completely bled off of all its charge. Okay, so let's now solve for the current as a function of time. So I will be equal to dq dt. And if you take the derivative of that with respect to time, then you end up with minus Q max over RC times e to the minus t over RC. Okay. Okay, now Q max, you could, if you wanted to, write that in terms of the battery that you initially charged your capacitor with. So if you initially charged your capacitor with a battery of EMF, funky E here, then the Q max would be equal to C times the EMF of that battery. And then you could write the current in terms of minus the EMF of the battery divided by the resistor, and write it that way if you wanted to, okay? Now the minus sign here, that just means that the current is flowing opposite in direction to the way that it usually flows. And if you were to plot the current as a function of time, then it would look like this. Okay. Okie doke. Now, lots of times folks talk about R times C as being the time constant. RC does have units of time. So here, tau is often referred to as the time constant of the circuit, and tau is equal to R times C. And you can see here that the time constant is the amount of time that it would take a discharging capacitor to get to 1 over E times its initial value, okay? And so they speak of the time constant as sort of an amount of time that it takes that capacitor to either, for a charging capacitor, get decently charged up, or for a discharging capacitor to lose a decent amount of its charge, okay? I talk more about that in another online lecture where I'm doing RC circuits and then doing example problems for charging and discharging capacitors in RC circuits. So I encourage you to check that out. Okay, so that's how to find the equations for charging and discharging capacitors. I hope you enjoyed it and don't have any questions, but if you do, let me know and I'll see you in class.